Hello friends, I am Snehal and we are studying differential equations. And today we will discuss first order equations reducible to linear form. They are also called as Bernoulli's equations. So let us start. Now the Bernoulli's equation or first order equations reducible to linear form, they can be written as dy by dx plus p multiplied by y equals to q multiplied by y raised to n. So this is the general form. Now you can notice that this is very similar to the first order linear differential equations, and in fact this equation can be reduced to first order linear differential equation by only one substitution. Let us see how. So the method to solve this equation is quite straightforward, and the method is divide this equation by y raised to n. So this is the first step. So let us divide this by y raised to n. So we get 1 over y raised to n multiplied by dy by dx plus p times y divided by y raised to n equals to this y raised to n and y raised to n in denominator, they get cancelled out, so we have this q. Okay, then if I cancel one of this y with y in numerator, I have p divided by y raised to n minus 1, and here we have 1 over y raised to n dy by dx, and this is equal to q. Then we can rewrite this as y raised to minus n dy by dx multiplied by y raised to, if I take this in numerator, the sign will be reversed. So I have 1 minus n multiplied by p equals to q. Now we are going to substitute v equals to y raised to 1 minus n. Okay, there was this plus sign. So carefully note down this substitution. The substitution is v equals to y raised to 1 minus n. So this term we are substituting v in place of this term. So if we take derivative of this with respect to x, see what do we get? dv by dx equals to, now this right hand side is function of y. So we need to use chain rule of derivatives in order to find the derivative of this right hand side. So let us use chain rule. So we have 1 minus n multiplied by y raised to 1 minus n minus 1. Okay, so this is considering that derivative with respect to y, because this is function of y, and chain rule says that we have to multiply this derivative with respect to y by dy by dx. So this is derivative of y with respect to x. Okay, so this 1 and minus 1, they get cancelled out, and we have dv or dx equals to 1 minus n multiplied by y raised to minus n times dy by dx. So if you look at this term, we have y raised to minus n multiplied by dy by dx here. So we have the same term here. That means we can substitute this dv by dx in place of this term. So this is y raised to minus n multiplied by dy by dx. It gives me 1 over 1 minus n multiplied by dv by dx. Then I can substitute this thing, let's call this 2, and this thing, let's call this 3 in this equation. So this is suppose the equation number 1. So using 2 and 3 in equation 1, I can rewrite the equation 1, which is 1 over 1 minus n times dv by dx. So in place of this term, I have substituted 1 over 1 minus n times dv by dx, plus we have y raised to 1 minus n, and y raised to 1 minus n is v. So this is p multiplied by v equals to q. Now if we multiply this whole equation by 1 minus n, what we get is dv by dx plus 1 minus n times p multiplied by v equals to 1 minus n multiplied by q. Okay, so this is the first order linear differential equation in terms of v. Now we can just rewrite this term and this term. So I can write that p prime equals to 1 minus n multiplied by p, and q prime equals to 1 minus n multiplied by q. So we get dv by dx plus p prime multiplied by v equals to q prime. So this is that same first order linear differential equation in terms of v. Now we know how to solve this. So what we need to do is find the integrating factor. So integrating factor is e raised to integral of p dx. Here it is p prime dx. And once we find the integrating factor, we can write solution in terms of integrating factor and v. And the solution is v times the integrating factor equals to integral of q times integrating factor plus c. So this is the solution in terms of v and integrating factor. Now this way we can solve this differential equation. So let us revise the method once. Given this differential equation, which is reducible to linear form, what we need to do is, the first step is to divide this equation by y raised to n, and then the next step is to substitute v equals to this y raised to 1 minus n. Okay, after that the given equation gets reduced this way to the first order linear differential equation. So this is the reduced first order linear differential equation, which can be solved by using the method of integrating factor, and this is the solution. So now let us try some problems on this method. So let me erase this. Okay, so let us see problem number 1, and it is dy over dx plus y over x equals to x multiplied by y square. So as per the procedure we discussed, we need to divide this whole equation by y square. So dividing by y square, we get 1 over y square multiplied by dy by dx plus 1 over y square multiplied by y over x equals to, if we divide this side by y square, we get x. Now this y gets cancelled out with the square, that means we have this y in the denominator. Then we can rewrite this equation as y raised to minus 2 multiplied by dy by dx plus this term is y raised to minus 1 multiplied by 1 over x equals to x. Now we need to substitute v in place of this y raised to minus 1. So let's do that. So substituting v equals to y raised to minus 1 in above equation, we get dv by dx equals to, now derivative of this we'll find out by using the chain rule, and it is minus 1 multiplied by y raised to minus 2. So derivative considering y is the independent variable, and then applying chain rule we'll have dy over dx. Okay, then let's take minus sign on the other side to match with this term, which is y raised to minus 2 multiplied by dy over dx. So we have y raised to minus 2 multiplied by dy over dx equals to minus of dv by dx. So substituting this and this thing in equation 1. So let's call this equation 1. 2 and 3. So substituting two and 3 in equation 1, what we get is minus of dv by dx, here minus of dv by dx plus y raised to minus 1 is b, so plus b multiplied by 1 over x equals to x. Then if we multiply the whole equation with minus sign, we get dv by dx plus v multiplied by minus 1 over x equals to minus x. So now we are able to convert or reduce this equation in linear form. So this is the Leibniz linear equation we have, and we can solve this by using the usual method. So let's do that. Now comparing with, now v is variable, so dv by dx plus p times v equals to q. We have p equals to, comparing this with this, we have p equals to minus 1 over x. So it is minus 1 over x, and q equals to minus x. Okay. Then, as we know, we need to find the integrating factor here. Okay. So do you remember formula for the integrating factor? Integrating factor is e raised to integral of p dx. So let's find the integrating factor. P is minus 1 over x. So let's substitute that. Or let's find this integral first. So integral of p dx equals to minus 1 over x dx. This integral. Now this integral is just if we take minus sign outside, is minus of log x plus the constant of integration which we set equal to 0. So we have minus of log of x, that is log of x raised to minus 1, we'll take here. Okay, this is minus 1 multiplied by log of x, and by using the rules for logarithm, we can write this as log of x raised to this term, minus 1. Okay, so we got integral of p dx. Let's substitute it here to find the integrating factor. So integrating factor is e raised to integral of p dx, which is e raised to log of x raised to minus 1, and which is, since the e and log, they are inverse functions, we have integrating factor equals to x raised to minus 1, or which is 1 over x. Okay, so now that we got the integrating factor, we can write solution of this equation in terms of the integrating factor. So let us write that. So solution, as we know, it is b times the integrating factor equals to integral of q times the integrating factor dx plus c. Okay, so let's substitute integrating factor and q here. So we get v multiplied by 1 over x equals to integral of q is minus x times integrating factor is 1 over x dx plus c, and this x gets cancelled out. So we are left with integral of dx with minus sign equals to integral of dx plus c, so which is minus of x plus c, and this is v over x. So we substituted y raised to minus 1 equals to v, so we can substitute it back. So since v equals to y raised to minus 1 implies that y raised to minus 1 or x equals to minus x plus c, or this is just 1 over y, so I can write this term as 1 over xy equals to minus x plus c. So this is solution of the differential equation in terms of x and y. So this is the method to follow when we have equations reducible to linear form. First of all, we need to reduce it to linear form and then use the procedure to solve the linear differential equation. So let us see another problem. Now let us try to solve the second problem. dy by dx minus y multiplied by tan x equals to minus of y squared multiplied by sec x. So let us follow the method we discussed, and method says that we need to divide this whole equation by y squared. So let's do that. Dividing by y squared, we get 1 over y squared multiplied by dy by dx minus y divided by y squared multiplied by this tan x equals to this y squared gets cancelled with the y squared with which we are dividing. So we have minus of sec x, this y gets cancelled out, and we have y in denominator, and therefore we can rewrite this equation as y raised to minus 2 multiplied by dy by dx minus, we have y here, so in numerator we can write y raised to minus 1 times tan of x equals to minus sec x. Okay, so next thing our method says is we have to substitute in place of this y raised to minus 1 v. So let us do that. The substitution is v equals to y raised to minus 1, and therefore dv by dx equals to derivative of this with respect to y multiplied by dy by dx by chain rule. So this is minus 1 multiplied by y raised to minus 2 multiplied by dy by dx. Okay, so this is the derivative. Then we have this term here, y raised to minus 2 multiplied by dy by dx, and we got the same term here also. So we can have y raised to minus 2 times dy over dx equals to minus of dv by dx. So we need to substitute this and this in this equation. So let's call this equation number 1. This equation is 2. This equation is 3. So using 2 and 3, we can rewrite the equation 1 using 2 and 3. In equation 1, the equation 1 becomes, using this, we have minus of dv over dx. Then in place of y raised to minus 1, we have v. So minus v multiplied by this tan x equals to minus sec x. So equals to minus of sec x. Okay, and we can get rid of this minus sign to have dv by dx plus v multiplied by tan x equals to sec x. Okay, so now we have converted or reduced this differential equation into a linear differential equation of first order, and we know how to solve this. So we just need to compare it with the linear differential equation of first order and find the integrating factor. So comparing with the linear differential equation, which is dv by dx plus p times v equals to q, we get p equals to tan x, okay, from this and this term. So p is tan x, and from this and this term we have q equals to sec x. So q is sec x, and next step is to find the integrating factor, and we know that the integrating factor is e raised to integral of p dx. So we need to find this integral, the integral of p dx. So let's do that. So let me erase this. We'll need this v. So let's note it here that v equals to y raised to minus 1. Okay, so let us erase this. Now integral of p dx equals to integral of tan x and this is simple integral to do because it is just sin x over cosine x dx. We can take u equals to cos x, so sin x its derivative, so this is simple to solve. So let's take u equals to cosine x, so du by dx equals to minus sin x, and therefore we can write du equals to minus sin x dx, okay, from here, and that's why sin x dx is minus du. So let's rewrite this. Integral of p dx equals to integral of minus du over u, and this is just log of u, okay, with this minus sign. So this is minus of log of u. We can take this minus sign here, or we can write this is minus 1 multiplied by log of u. So by using rules of logarithm, I can rewrite this as log of u raised to minus 1. So this is this integral. And then u is cosine x. I can use that. So this is log of cosine x raised to minus 1, which is log of 1 over cosine x. Okay. Now using this integral of p dx, we can find the integrating factor. So let us use this. So we have integrating factor equals to e raised to integral of p dx, and that is log of 1 over cosine x. So e raised to log of 1 over cosine x. Now e and log, they are inverse functions, so they cancel out each other's operations, and that's why the result of this is the integrating factor is just 1 over cosine x. Okay. So now we got all the information to find out the solution. Now let's find the solution in terms of integrating factor and v. So we know the formula. The solution is v multiplied by integrating factor equals to integral of q times the integrating factor plus c. Now let's substitute the values of integrating factor and q. So we have q equals to sec x, and integrating factor is 1 over cosine x. So v multiplied by 1 over cosine x equals to, this q is sec x multiplied by integrating factor is 1 over cosine x, that is sec x, plus c. So this is sec x multiplied by sec x, sec square x dx plus c, and since sec square x is derivative of tan x, integral of sec square x is tan x. So its integral is just tan of x, and we have the c here. So this is v divided by cos x. We can multiply throughout by cosine x to get v equals to cosine x multiplied by tan x, and tan x is sin x over cosine x, plus c multiplied by cosine x. So this cosine x and cosine x gets cancelled out. So we have v equals to sin x plus c times cosine x. Okay, this is the solution in terms of v, but we want solution in terms of y. So we can have that using this substitution. So let us substitute this back. So we get y raised to minus 1, which is 1 over y equals to just sin x plus c times cosine x. So this is the required solution. Okay. So this is how we solve the equations reducible to linear form. Next time we will see the exact differential equations of first order. Till then, try some problems on methods we discussed so far. Thanks for watching.